A 1% storm doesn't automatically produce a 1% flood, yet many designs may still assume that. In hydrological modeling, we often use the term design storm and design flood as if they mean the same thing, but they don't. One is the meteorological input while the other is the resulting catchment output. And confusing the two can lead to undersized infrastructure, inflated costs, and completely inconsistent flood risk estimates. In this video, I will unpack the difference and show you why it carries far greater implications than most engineers assume. Let's get started. A design storm is a statistically defined rainfall event. It is described by its depth, duration, temporal pattern, and probability, such as a 1% annual exceedance probability event. Design storm is a meteorological input to a model. A design flood, on the other hand, is the hydrological output, the resulting peak discharge or full hydrograph produced by the catchment. It can be derived either by transforming a design storm through a rainfall runoff model or by a statistical analysis of observed streamflow data. The confusion begins when we assume the probabilities automatically match. This is known as the probability neutrality assumption. Many practitioners assume a 1% AEP storm produces a 1% AEP flood. This is known as the design event approach. But the flood magnitude depends heavily on catchment conditions, especially antecedent soil moisture. A 1% AEP storm on dry soil may generate only a 5% AEP flood, while the same storm on saturated soil may produce a 0.5% AEP flood. Rainfall probability and flood probability are not inherently identical. Another common confusion is between time of concentration (TC) and critical storm duration. Time of concentration is the travel time from the most remote point of the catchment. On the other hand, critical duration is the storm duration that produces the maximum peak flow. In simple rational method application, TC is often used as a proxy. But in complex catchments with significant storage or unusual shapes, the critical duration can differ significantly from TC. Misinterpreting this can lead to either undersized or over-designed systems. If you'd like to know more about the time of concentration or critical storm duration, please watch our previous videos on this topic. The other confusion is about the storm temporal patterns. Rainfall is rarely smooth in reality, but synthetic design storms often are. There are three technical traps here. First is the average temporal patterns. Older approaches often relied on a single representative pattern derived from averaging historical storms, which smooth out intense bursts. But real convective storms are highly peaky, and a smoothing can underestimate the true runoff peak response. The second one is embedded burst. This is more subtle and more dangerous. Imagine running a 1% AEP 120-hour storm. If the chosen temporal pattern places 50% of rainfall into a 3-hour window, the 3-hour burst may statistically represent a much rarer event, perhaps 0.1% AEP. So, although you believe you are designing for a 1% event, the model is being driven by a much rarer embedded burst. This makes the design criteria inconsistent and overly conservative for the intended risk level. The last one is catchment sensitivity to peakedness. In small urbanized areas, short duration, high intensity peaky storms are typically critical. In contrast, large rural catchments are more sensitive to long duration, lower intensity events where total runoff volume is the driver. Confusing design storm and design flood in practice can lead to the following issues. First, underestimation of flood risk. Second, infrastructure failure due to incorrect critical duration. Third is the unnecessary capital cost from overly conservative assumptions. And finally, misleading flood mapping when relying purely on synthetic storms. Modern practice increasingly shifts towards Ensemble and Monte Carlo approaches in which multiple temporal patterns and catchment states are evaluated to better represent the true flood probability. Because in reality, flood risk is not driven by a single deterministic storm, it's driven by variability. A design storm is the input rainfall. A design flood is the output runoff. They are related but not similar. When we assume their probabilities are similar by default, we simplify a fundamentally nonlinear system. A good hydrological modeling begins by respecting this difference. If you like this video, please share it with others. Thank you for watching, and I will see you in the next one.